So these are three different fields: thermodynamics, in particular axiomatic thermodynamics, decision theory, and quantum mechanics, where entanglement is being studied. And what is, I think, the basis of this mathematical analogy is that in all of these cases, people are working with a sort of weak ordering relation, which is technically known as pre-ordering, which is a relation between elements of a certain set that satisfies these two properties, transitivity and reflexivity. That's a very weak ordering structure, so in particular it does not imply that the order is complete, total, which would mean that for any two elements of that set, you would have that relation one way or the other way around, nor even that it is a partial order. That's also restricted. Now, when we talk about quantification of such an order, that means that we are trying to find a function which respects it. In a certain sense, ideally, we would like to find a function such that if the value of the function defined on the elements of that set satisfy the equality, then that would be equivalent to that relation. Now, clearly, I hope you see from the start that if I only use this very weak ordering relation, such a statement can never hold. Why? Well, functions are real valued functions, at least, are always totally, completely ordered. The values of them, because their values are real numbers, and real numbers are completely ordered. So if this equivalence would hold, that would mean that this would have to be a complete order too. But I've only assumed that it's a very weak ordering relation. So something has to go if I nevertheless want a statement that is similar to this. And now you can go two different routes. You can simply add further assumptions or axioms to your weak relation. Or you can try to find a weaker statement. Or you can give up the equivalence one way or the other. But I will argue that the most powerful result you can obtain in these studies is always to maintain the equivalence relation, so that you would have a representation theory. You have a question?
Yes. You have there the word reflexivity.
Yes.
The famous financier George Soros has the same notion of reflexivity. I don't know if you're aware of that or not. His famous book called Alchemy of Finance. So I was wondering if you borrowed that word from him or he borrowed it from you.
No, I think if a relation is such that each element has it to itself, it's quite standard usage to say that that's a reflexive relation.
So it's not something you invented?
No. I'm trying to use standard. Now, let me look at thermodynamics. I hope you have at least some familiarity with thermodynamics from your college days, and then you might remember that there was a theory about steam engines and Carnot cycles, and in the end there was some differential theory about how entropy was connected to heat exchange. Well, that's all very fine, but that was a 19th century theory which actually was never formulated in a very rigorous manner. And Elliot Leap and Jacob Ingvarsson have relatively recently tried to give a sort of rigorous mathematical foundation to that theory. And I want to tell you a little bit about their axioms. It might seem rather formidable and formal, abstract, but I hope I can explain it in just a few sentences. So, like any physical theory, it operates with the notion of a state space. These are possible states that the physical system, the thermodynamic system in this case, can be in. And we will only consider equilibrium states of such a system. That is, states which can be characterized completely by ordinary macroscopical parameters like volume, temperature, pressure, etc. You can combine such systems to form a composite phase space. And composition here means nothing but just mentally considering two systems to be part of a larger system. It doesn't involve any type of interaction between them. You can just put them side by side and say, I've got a larger system. And so the state of that larger system would be Cartesian product of the states of the separate systems. Another operation which they conceive of is what they call scaling. That means that for any system in the state X, you can find another system which is, so to say, twice as big if L happens to as the original system. And that means, if it's gas, for example, that that bigger system would simply have twice the amount of matter, twice the amount of energy, twice the amount of volume, but at the same temperature, at the same pressure, etc. So this is where traditionally you would have to use this distinction between extensive and intensive variables. But I hope that at least conceptually it's clear what's being meant here. This is just a mental note to remember that this phase space is different from the original phase space. And then the central notion is the relation we're talking about. So, if we have two states of a particular system, okay. If you have two states of the same system, you can ask yourself whether you can transform one state to the other by an adiabatic process. And if the answer is yes, then you will write the result in the form of this relation. If the answer is no, then that relation does not exist between those two states. So now we can lay down a couple of, this is an axiomatic approach to thermodynamics, so we can lay down a couple of properties we want that relation to have down in the form of axioms. And so the first is really rather simple. It means that if you do nothing to your system so that it remains in the same state, that will be an example of an adiabatic process. So this relation holds between the states and itself. Therefore it's reflexive. It's transitive because if you can find an adiabatic process from X to Y and another adiabatic process from Y to Z, then by composition of these processes you can find a process which goes from X to Z, etc. If you can find an adiabatic process on one system and another adiabatic process on another system, then if you combine these two systems in a larger system, you can also find the accompanying adiabatic process to get to the composite final state. Adiabatic accessibility is, if you like, if you will, it's invariant on scaling. If you can do something for 1 mole of gas, you can also perform a similar transformation for 2 moles of gas. You can split the system into subsystems, say by letting down a partition in the middle, so you get 2 halves of the original system. That is an adiabatic process in thermodynamics. And then lifting the partition again is also an adiabatic process. So here I have the relation holding both ways, and for that special case I use the real. The only axiom which might involve, I think, a little bit of thought is what they call the continuity axiom, which means that if you have a system, and by adding just a little bit of another system, you can perform some adiabatic process to a final state. Oh, so sorry, this plus should have been a comma. This is normal notation. And be able to transform this state into that state. And you can do that no matter how small the epsilon is. Then, well, the argument goes, then that second subsystem should have been irrelevant, and you could have also performed the adiabatic transformation directly from the first subsystem from X to Y. Plus, to end this long list, there's one more special assumptions they need in their work, and this is not an axiom, but it's something they call an hypothesis, comparability hypothesis, which, as you can guess from its name, has a much weaker status than the other axiom. And what does it say? Well, that for any two states in the same state space, you can either go from X to Y by an adiabatic process, or else you can go from Y to X by an adiabatic process. That means that, in fact, the ordering relation we're talking about is not just a pre-order, as is stipulated in the first two axioms, but it actually is a complete order relation. So this is a much stronger assumption. But anyhow, suppose that we make it. Then Lieb and Ingvarson are able to prove a very nice theorem which says that if these axioms hold and the comparability hypothesis, then you can find a function S, which we will call entropy, which has the following property, that whenever there is an adiabatic transformation from X to Y, two states of the same subsystem, or same system, then you can characterize that by saying that the entropy in the final state is larger than the entropy in the initial state. So in a sense, this captures completely the physical idea of the second law, stating that entropy always increases in adiabatic processes. And it's an equivalence relation, which is very nice. And moreover, the function S is almost unique up to a finite transformations. And it's additive and extensive, which means that you can express the entropy of a composite system in sums of a linear sum of the entropy of the subsystems. So, a marvelous result. And, well, just speaking from the background of thermodynamics, I do think this is a marvelous extension of all these previous 19th century expositions of entropy, because the presentation is so much more general. So, for example, you don't even need to assume that your state space is a differentiable manifold. And so you won't necessarily be able to introduce differentials on your manifold. And that means that you can use these axioms of this approach even in cases where a notion like ds is TdQ, as is one of the traditional formulas, simply fails to make any sense. And so this approach will also hold for very weird thermodynamical systems, or indeed not so weird thermodynamical systems. You only need to assume that there is a phase transition in the system, and differentiability already goes out the window. I should, but I don't want to insist too long on this, actually also point out that Lieb and Ingvarson have a slightly more liberal notion of an adiabatic transformation that is usually used in textbooks. And so the most general concept of an adiabatic transformation is if it's possible to change the state from x to y by means of an interaction with some auxiliary device and a weight in such a way that the device, the auxiliary device, returns to the initial state at the end of the process, whereas the weight may have changed its position in the gravitational field. So the inclusion of this weight is obviously there to guarantee that either you might do some work on the system or the work might do some system, and the system might do some work, and it's stored in the height of this weight, in the gravity field. But otherwise, you might use any device you like to interact with your system under the condition that that device is brought back in exactly the same state in which it started. And this is much more general than the traditional notion of adiabatic, which would mean any process you can perform on a system without exchanging heat with the environment. But anyway, this is just a side remark. What I do want to stress is the result is nice. It relies on the comparability hypothesis, which is the strongest assumption and also physically perhaps the most dubious, because, well, it's not so clear at all that for a general physical system, thermodynamical system, it's always possible to find an adiabatic process that can take you either one way or the other way between two given states. And actually, Kliman and Ingvarsson admitted and assumed that comparability only holds for what they call simple systems. So the result is actually restricted physically to simple thermodynamics. But, as I said, the result is an if and only if statement, and therefore it's really a representation theorem of this particular adiabatic accessibility.
When you say it's equivalence in the sense of equivalent relation, it's not equivalence relation, or
Equivalence does not refer to the relation, but to the statement between the relation and the inequality and functions.
it's not an equivalence relation.
No, it's not an equivalence relation. It's a representation theorem in the sense that if you want to know whether there is an adiabatic process that goes from x to y, then you only have to calculate the values of these functions, and then you can already tell. And okay, quantum theory. I'm not sure whether you're familiar with quantum mechanics. I hope a little bit. But quantum theory, we have a completely different notion of state. States are now represented by quantum states, which in the most general form are density matrices on the Hilbert space. And if you have a product system, then if it's separable at least, then its state will be the tensor product of the density matrix of the separate systems. But in general, the state space is closed under convex combination. So the most general state of a composite system might actually be a much more general notion. And if actually that state could be written as a convex combination of this form, that is to say, product density matrices of the two subsystems, and then some numbers which lie between 0 and 1, which add up to 1, then that state is so-called non-entangled or separable. And the curious point is that quantum theory has states which do not have this form, which are therefore entangled and which are the subject of the most intense investigations nowadays. because they can do all kinds of non-classical, can be used for all kinds of non-classical information tests.
I don't know if that should be PI or OI. The subscript. Subscript.
Okay, yes. Yeah. I'm sorry about that. Now, something that interests people who study entanglement is the question not only whether states are entangled or not, but also how much entangled they are. So they want to find some measure of the extent of entanglement. And the first thing to note, perhaps, is that entanglement is at least invariant under some types of operations. So you can perform unitary or a product of unitary operators on the state composite system, which is what this expression does. Then entanglement will not change. If the original state is entangled here, then the final state will be entangled. If it's not entangled, then this state will also not be entangled. And so this means that there is at least some class of operations which clearly will not influence the amount of entanglement in the system. But let's look at the question of when states are very entangled and when they are not entangled, and see if this can vary continuously. Well, the simplest case is if the density matrix is a so-called pure state, in which it's just the product of the bra and a ket factor. And the famous example is the state that we know from Einstein-Podolsky-Rosen paradox, the Bell inequalities. It's so-called singlet state. Don't mind the technicalities here now. This is a state which is well known to be maximally entangled. But you can vary the coefficients in front of these two vectors here, so they have different values. And then, well, if alpha goes to 0 or 1, then only one term survives and you have a product state, which is not entangled. And if alpha has the value 1/2, then you're back to this state, which has maximally entangled. And so you can see that entanglement, at least for these pure states, will be a function of alpha, which is maximal if alpha is 1/2 and 0 if alpha is either 1 or 0. Now, the main idea in this field, the main intuition that most researchers have, or it could also be expressed as a theorem if the appropriate concepts are well defined, is that there is a class of operations called LOCC operations, which will definitely not be able to increase entanglement. What are LOCC operations? Well, it's very hard to give you a mathematical definition, and I'm sure you will not learn much from it. But, technically speaking, it's about all the type of state transformations you can perform on this composite system, which are achieved by local operations, so if the two systems are far away from each other, you can do something to this subsystem, make a measurement, let it evolve by some local dynamics, have it interact with the third system, etc., etc. Do something similar to the other subsystem, which is far away. And you can even use classical communications, that is to say, Alice, which is over here and performs her measurements, can telephone Bob on the other side about the outcomes she obtained and say, oh, I found this result, therefore you should make this measurement. And Bob says back, oh, I made this measurement, I found that result. Therefore, would you please perform that dynamical operation, etc., etc. All that is allowed. And yet, by all these however clever Alice and Bob are in this way, whatever they can do to their subsystems of the total system, in no way will this lead to an increase of entanglement. It can only lead to a decrease of entanglement. So now the question is, when is it possible to find, when is it, if you have two quantum states, when and when not is it possible to find an LOCC operation from one to the other? And notice that this problem now seems a little bit much like the problem that Liebig-Ingvarson studied in thermodynamics. Well, there is a theorem. This is sort of the basis of the theorem. Suppose you have a pure state, pure product set, a pure state of two subsystems. Then it happens to be the case that you can always find two basis factors in their factor Hilbert spaces, such that that state can be written in this form. This is so-called Schmidt decomposition. These are product states, and these are just numbers which squares of which add up to 1, and they're called Schmidt coefficients. And if you look back at the previous slide, when we had the singlet state, you will have noted that if both of these coefficients were equal to 1/2, then you would have maximally entangled. If they happen to be 0 or 1, they would not be entangled. Now, the important theorem here, found by Michael Nielsen, who actually still lives in Waterloo, I believe, is that you can find an adiabatic, an LOCC transformation from one pure factor state to another pure factor state for a constant system in terms of the Schmidt coefficients of these states, and these can also be thought of as a probability distribution because they're simply numbers whose squares, they're simply numbers that add up to 1, and they're lie between 0 and 1. And there is a next relationship holding between these probability distributions called minimization. So if you have one distribution or one set of Schmidt coefficients, P, and another set of possible Schmidt coefficients, Q, then if it's the case that you can write one of these numbers as a convex mixture of permuted versions of the other ones, then that relation holds. That is to say, P is modularized for Q. And so, the question, whether you can find an LOCC operation that transforms one state in the other state, is judged completely by the question of whether, if you can look at the Schmidt decomposition and then ask yourself whether this particular pre-ordering between Schmidt coefficients. So, if that's the case, then any measure of the extent of entanglement, at least for pure states, should actually be determined by that particular pre-order on the Schmidt coefficients. And there are, of course, simple expressions that do that. The most famous is the von Neumann entropy of the state. And this, if you write that in terms of the Schmidt coefficients, actually is identical to the well-known Shannon entropy for the Schmidt coefficients. But one can still ask whether that expression is unique. Are there any other measures that would also be capable of playing a role as a measure of entanglement? What shall we do about mixed states? Because all of this simply is is still studying the special case of pure states. And, well, as you probably have noted, there seems to be a quite strong analogy here with the approach of Liebman-Ingersoll in thermodynamics. And so you could ask yourself, does minorization, which is the notion, the weak order relation you have here, is that actually an instantiation of the axioms that Liebman-Ingersoll imposed? And if that would be the case, then you could take these LOCC operations that are completely analogous to adiabatic operations in thermodynamics. Now, there's good news and there's bad news. Obviously, in all these cases, we are dealing with pre-orders. So the first two axioms of Liebman-Ingersoll clearly satisfied for priorization, and therefore for, let us call it LOCC accessibility. And if you interpret the combination in thermodynamics as taking a product state in quantum mechanics, so you have this type of correspondence, then all the other axioms seem to hold too, at least some of them. But nevertheless, as I said, there's bad news. There are two main exceptions. The first is that sometimes it might happen that you cannot find an LOCC operation which turns from one state to another state, but nevertheless, if you add a third system to the whole system, and if you ask yourself, can I transform this state into that state, then such an LOCC operation does exist. And it's somewhat of a miracle because omega itself doesn't change in this process. And so people have called this, with the obvious analogy with chemistry here, catalysis. Sometimes it's possible to transform psi into psi prime, not directly, but if you add another system which acts as a catalyst, then that transformation is possible. And the catalyst doesn't change its state over here. Now, in fact, it might not be completely obvious, but there is a theorem derivable from the Liebman-Ingersoll approach which says that that could never happen. So, catalysis is certainly a violation of the Liebman-Ingersoll. More importantly, for my purposes, the comparability hypothesis doesn't hold. That is to say, minorization is, except for the simplest case of two-dimensional systems, is not a complete order. It's really a weak pre-order. It's not even a partial order. And therefore, comparability hypothesis, which imposes that the pre-order would have to be complete, simply does not hold. And therefore, you can't apply the Liebman-Ingersoll theorem. This is not an instantiation of the because of these two problems. Now, the first problem actually has a solution, which was also found by Michael Nielsen. That is to say, well, if such a phenomenon holds, then we shall simply define a slightly stronger pre-order, which takes account of the fact that sometimes by adding another system to your system, transformations are possible which would otherwise not be possible, even if that additional system is returned to the same initial state. So, we simply define the relation between, say, two probability distributions, P and Q, which we now call trumping, in the sense that, which holds just in case if you can find another distribution, Z, which you can add to these other two probability distributions, and in the sense of taking an independent product of these two. And if the minimization relation holds for these two, then P is trumped by Q. So this is a relationship which obviously holds if Q is marginalized by P, but it holds also in slightly more general cases, and therefore it's a stronger pre-order. Right? So that's what it says here. Marginalization implies trumping, but not the other way around. So, you might now think, well, okay, let's try this slightly stronger pre-ordering relation and see if the Leap-Ingvarson approach, Leap-Ingvarson axioms are applicable in that case. Well, it turns out that in that case you have complete success. At least you can find that all the axioms are fulfilled. So that's very nice. And in fact, there is also a maximization theorem. Sorry, there is a representation theorem for trumping. It is found by two people working independently of one another, Tilkut and Klimesh, just a few years ago. And apart from some technical assumptions here, it says that trumping between two probability distributions, discrete probability distribution, holds if and only if for a whole family of expressions which depend on the parameter R, there are appropriate inequalities between P and Q. The nature of the inequalities depends a little bit on the choice of the parameter R, but that's just cosmetics. The important point is, trumping holds if and only if for a whole family of expressions you will have the appropriate inequality relations. And these expressions are slight variants of what is well known as Gradients. So these are entropy-like expressions on the probability distribution. So actually you have to take a logarithm of them and just slight change in the parameters. But the important point is you have a representation theorem that tells you that you can still perfectly characterize when that pre-ordering relation holds. But what you have to give up now is that you would try and find that characterization in terms of a single inequality for a single function. Instead, you would have inequality in a whole family of functions. In fact, you get additivity and extensivity also for free, as in the Leap-Ingvarson case. You can simply prove that this result also is obtained. So why do we only get this much weaker result, that there is inequality in a whole family of entropy-like expressions? Well, that's clearly due to the fact that even if you have extended the relation into the majorization to trumping, and you've solved one of the two problems I had in the bad news slide, you cannot get around the fact that it's still a pre-order and not a complete order. So the Leap-Ingvarson comparability hypothesis simply fails, and there is no way to remedy that except if you only want to limit yourself to the dimensions. So, we've got a class of measures which do not only characterize trumping, but thanks to the definition of Elon operation, also characterize completely when it is possible to transform one quantum state to another quantum state by local operations and classical communications. If only you also allow yourself the possibility that maybe sometimes you would need access to an auxiliary quantum state, in a state omega, as long as you promise to bring that system back in exactly the state omega at the end of the operation. And notice also how close that is to the intended interpretation of Lieb and Ingvarson when they said an adiabatic transformation is something you can do to a system with any auxiliary device as long as you promise to bring that auxiliary device back in the exact state in which you found it when you started to use it. And the other thing as well, something I think I've already said, comparison hypothesis has been called, and apparently this has the consequence that you can't find an equivalence, a representation result you will have to use. So the entropy is not unique. There's a whole family of entropy lines. Now, finally, I also mentioned decision theory. Perhaps this is a field which is more familiar to many of you, but let me try and give a very pedestrian characterization. This has nothing to do with physics, let alone quantum physics. We're dealing with a rational agent which is faced with certain decisions. In the simple case, he wakes up in the morning and has to decide what clothes to wear or where he's going out. And so you might think, well, if the weather is nice, I would prefer to wear a simple t-shirt, but if the weather is horrible, then I will do a warm raincoat, protect myself against the rain and wind. And now, since he doesn't know what the weather will be, he's faced with certain outcomes of his decision. So he might be wearing a t-shirt and the weather is really nice, so in that case he's happy. It could also be that the weather is pouring and it's freezing outside and he still made the decision to wear only a t-shirt, in which case I presume he's not so happy. And then there are two intermediate cases where either he's the weather is nice and he has on his hot coat, or the weather is terrible and he is wearing his hot coat, and I'm not sure whether he would be happier. In each of these cases he would be happier. But anyway, decision theory assumes that you can order these outcomes in terms of a preference relation. Some outcomes are nice, some outcomes are less nice. And so the rational agent is supposed to have a preference relation, preference ordering of the outcome. And you can also extend that to so-called mixtures of outcomes, or gambles, in which you, if the agent has certain preferences in outcomes S or T, you might propose to him a gamble in which says, oh, with probability alpha, you're getting outcome S, but with probability 1 minus alpha, you will get the other outcome T. Now tell me if you prefer that against other outcomes. And supposedly, a rational agent will be able to evaluate his preference for such gambles as well. Now, in this field too, there's a famous representation theorem by von Neumann and Marcuse. And in a nutshell, it basically says the following. Once you suppose that the preferences of a rational agent are completely ordered, that is to say that preference is complete order, then you can find a function that represents that preference, and that function is traditionally called utility, in such a way that the agent prefers T above S just in case the utility of T is larger than the utility of S. And this looks very much like the Leib-Nicolson approach. And in fact, mathematically, you can show that von Neumann-Morgenstern theory was actually already stronger than the Leib-Nicolson approach, even though the latter was developed only in 1999 in the field of thermodynamics, which was apparently so far off from decision theory that they never thought of looking at theorems which were derived half a century earlier, but it really failed. But now, funnily enough, also in this case, we are getting problems with this assumption of complete order. So many economists have wondered, well, is it really constitutive of rational agents that their preferences between possible outcomes should always be completely ordered? That is to say that for any two outcomes, the agent can always say, oh, I either prefer this one to that, or the other way around. Well, it's sort of intuitive to me, and I guess also to you, that that's actually a very heavy assumption. There might be many cases where people are simply undecided. They say, oh, I definitely, so like the effect like the previous slide. Of course, this would be the ideal world, and this would be the worst outcome I can think of, but whether I feel more happy in these two intermediate cases is actually not so clear to me. So I could very well imagine having only a preference relation which is not defined for any pair. So in that case, you would not have a complete ordering, but only a partial ordering, or perhaps even only a pre-ordering. And not only does that seem psychologically more natural, it's also a situation which appears quite often if the decisions are not being made by an individual but by a group. And now, to accommodate that, say, drawback of the von Neumann-Morgenstern theorem, there has recently also been an extension of that theorem, in which we only assume that preference is a pre-order relation on some set. This is not a physical state space, but a state outcomes of the decision. And, well, there are some technical assumptions, which if you have the time I was going to skip on. But let me just mention that they are actually weaker than the formal other assumptions that Leib and Nicolson assumed in their 6 sections. Can't read it.
5 minutes.
Okay, yeah. But the upshot of this theorem is that you only assume that there is a pre-order relation. It's not a complete order. And then still, you can find a representation theorem which says that, oops, it just fell off the bottom. The main line is that this holds, but now not for a unique or a finally unique utility function, but for a whole family of utility functions. So if this holds for every u in this particular class curly u, then that preference will be. Which means that you can still have a representation theorem for a pre-order relation. The only thing you can not hope to find is that you represent that pre-order relation by a unique real-valued function. Now that, well, I basically said this result, let me perhaps go to it. Well, let me say one more thing. This result is also an axiomatic result. I mean, you don't need to specify anything about the meaning of this. And so, funnily, you can apply this in quantum mechanics. It's one of the rare cases where a result found in decision theory is actually has useful results in these esoteric fields from quantum mechanics. So suppose these are quantum states, and suppose this is the Elon accessibility. Well, then all the assumptions of the theorem hold. And therefore, you can already be sure that if you can transform a quantum state from X to Y by local operations and entanglement intelligence, then there must be a convex closed class of entanglement measures which represent that relationship in just the right way. So, there seems to be a sort of rather general and in my eyes rather striking analogy between methods which are used both in thermodynamics and in quantum theory and actually in utility theory. And what the important thing that we've learned is that if that ordering relation, which is the core of all these problems, if that is not complete ordering, then, well, as I already started out, it's almost silly then to expect that you can represent that ordering in terms of the values of an inequality between the values of a real single real value function. And although some people might think, oh, but uniqueness is rather nice because then I only have to calculate the value of a single function. The virtue of the type of theorems we've been looking at here are that they're representation theorems, and therefore they characterize the order relation completely. Now the price you have to pay for that is that you would have to calculate the values of a whole family. I personally think that's a small price to pay, because if you would go the other way, the other route that many people have done, say, simply add more and more axioms, so that finally you can turn down the whole class of such entropy-like expressions to obtain only, to narrow that down until there's only one single measure left. Well, then you have done yourself a favor by saying, oh, I have to look all the values of a single function. But you have lost the representation theory, because by comparing the values of these functions, you are not sure whether this ordering relation. And the last thing I want to stress once again is it's rather neat that these results from decision theory and in fact economics can be applied in quantum theory. And so this is one of the rare cases where maybe say that the alpha or the gamma sciences could actually influence and form as pre-runners of results in physics. And with that note, I'll stop. Thank you.
The family of entropic measures in the decision theory representation, if I'm not mistaken, was an infinite family.
Whether there's an infinite family?
It was an infinite family, is that correct?
Yes.
So in practice, you can only test a finite number of inequality. So how does one use a result like that in practice? Don't you need to continue searching until you find or prove that there exists a finite set of necessary and sufficient conditions for the interconversion to be possible?
Well, let me say two things. I don't feel so impressed by or inclined to agree that you can only test a finite number of inequalities. What you really, once P and Q are given, then these are really both functions of R. And what you would have to do is simply plot that function of R corresponding to one probability distribution, and then plot the other function for another distribution, Q, and you simply have to look at whether the graphs, if one graph is completely above the other graph, or whether they intersect somewhere. And that's not a task which is impossible to achieve in practice. The second thing I could say is that yes, in this case, we have an infinite class of expressions, but the theorem by mentioned here by Shapley-Bauzels made one more stipulation, and that is that it is a convex class. That means that even though the set of measures might be infinite, the infinite cardinality, if it's a convex set, it would suffice to look only at the extreme points. And it's very well possible that in many cases the class of extreme points is finite. And that would be sufficient to determine what the relation is.
In this case, it is unknown whether the set is finite currently?
In the case of this theorem?
Yes.
Well, this is an axiomatic theorem, so I should have stressed that more. In both the case of Lieb-Ingvarson and in this case, in decision theory, the approach is axiomatic. That is to say, these relations are only defined in terms of whatever you stipulate about them, but we don't actually know what case we're talking about. So it could be finite, could also be infinite. In quantum mechanics, the situation is slightly different because there the relations I'm talking about by LHC operations and so on are exactly and explicitly defined. So it's not a matter of imposing a number of axioms, rather it's in the question of showing by means of a theorem that certain properties are actually obtained. But there's always this distinction between axiomatics and an instantiation of some axiomatics. In the abstract state, you cannot state definitely whether it's finite or an infinite.
But in the finite dimensional quantum case, that's just probability measures in Rn, which is a simplex, that's convex, right? So
yes.
It's a nice space to work to.
Whenever you use the word entropy, are you referring to physical entropy or information entropy?
Aha! I was trying to refer to entropy-like expressions. I haven't been talking explicitly about information theory. I have been talking about thermodynamics, in which case entropy really meant old-fashioned thermodynamical entropy, as it is related to heat exchange in the steam engine. Of course, when I was talking about quantum mechanics and the memorization relation on probability distributions, I was talking about the Shannon entropy, which I can just look at as a mathematical notion. And of course, it has nothing to do with thermodynamical entropy. But nevertheless, that's what I was trying to make. There's an analogy between these concepts. But I would never go as far as to try and say that that informational entropy is identical to physical entropy, or the other way around. There's an analogy between similar notions which crop up in different fields of study, and their structural properties seem to be quite closely related.
Any other questions?